I'm going to follow up on what Carl did, and at the end of this, I'm going to try to take you through a little thought experiment, which I actually did, because it's useful to be quantitative about some of these sort of things about the ionosphere. As Carl showed you, it's very easy to assume that the ionosphere is nice and smooth because our monthly median models of that, including things like the International Reference Ionosphere, are in fact smooth because they've had a lot of the wiggles averaged out of them. But we know observationally that the case is, as Carl has also shown, that there's a lot of variability. And in fact, the encouraging thing for this community is that identifying the sources of that ionospheric variability and what is important at what time is a frontier science topic. If you go to the American Geophysical Union, we have talks all the time about ionospheric variability. It is something we're still learning a lot of. So I think this community can help a great deal. So just stepping back to the physics a little bit, what's going to make that variability that Carl talked about? Well, there's some things we know and things we don't. This is a classic sort of trigger for things we know. We know that in the auroral zone at high latitudes, for example, during storm times, you can get precipitation coming in, and that can do things like joule heating, stir up the atmosphere and heat it. And so this particular cartoon here from Gerd Prohl's review paper back in 2011 shows you that actually when you get the AE index, which is an auroral electrojet index, it's an indication of auroral activity. When that goes up and you get heating, you can actually get a bulge in the neutral atmosphere, which, because it's a little localized place, can launch a traveling atmospheric disturbance. And that moves in the form of acoustic gravity waves. This isn't the gravity waves that the LIGO project, for example, talks about. These are gravity waves where the restoring force is gravity. Think about a buoyancy wave. Well, that traveling atmospheric disturbance can move down, for example, toward the equator, and sometimes it comes from both poles and collides at the equator and does cool things. But anytime you disturb the neutral atmosphere, for something like traveling atmospheric disturbances, because there is neutral ion coupling, you're going to transfer that to traveling ionospheric disturbances. And one of the primary things that can do is make the F region vary in electron density. And we're going to be talking about electron density in this talk. There are other parameters that also vary, like velocity and plasma temperature. So this is one sort of classic way that people think about how TIDs get generated. You get heating at high latitudes, and then you get a wave structure that will travel from there. But the community over the last 15 or 20 years has realized that there's another source of space weather, if people will say space weather from below, which is that the lower atmosphere, the domain normally of meteorologists, is always generating acoustic gravity waves because of things, as we'll see, like wind blowing over orographic features like mountains or over waves. And as you go up and the atmospheric density gets lower and lower, those oscillations get bigger and bigger until they can break. And so things like tides, 12, 24-hour tides, planetary waves, several day oscillations as these waves wrap around the planet, seasonal variations, all of those are creating acoustic gravity waves, and these are just normal modes of the atmosphere if you dump a bunch of energy into them. Those transfer itself, it turns out, all the way up into the ionosphere, and that is where the frontier is right now. We don't necessarily entirely fully understand those coupling dynamics, but we do understand observationally pretty well what the amplitudes of the TIDs we observe are and some things about their wavelength. For those of you who aren't familiar with the various layers, I'm going to be referring to the neutral atmosphere here, starting at the troposphere, where I'm talking to you from, up into the stratosphere, mesosphere, and then into the thermosphere, which is sort of overlapping with the ionosphere. And then down here, we have the ionosphere with its various layers, F2 layer that Carl was mentioning, down to F1, E, D. And it changes from day to night. So gravity wave propagation. This is a very sophisticated fluid simulation with many factors. Just came out this past year by Eric Becker and Sharon Vadas. This shows you that the gravity wave propagation up from the ground is pretty complicated. It turns out that down at the bottom, you have primary gravity waves that are generated by mountain water flow. They go up and they break. They generate secondary gravity waves up in the mesosphere and the stratosphere, 30, 40 kilometers up to say about 90 to 100 kilometers. That's how the energy is dissipated from the primary waves. Those break. And then you get tertiary gravity waves, which then go way up into the thermosphere, where they start making the ionosphere move around. So there really are waves all the way up. And we know from these simulations and from some observations, tough to observe the neutral atmosphere, And we're talking about periods of 1 to 2 hours, several hundred kilometer wavelength, but 1 to several percent amplitude. As this particular plot from the paper shows, this is relative density perturbations, and this is a percent scale, and you can see 1 to several percent variations here, reasonably organized. So there, the thermosphere, and hence the ionosphere, is being really modulated by these sources. What do we see when we look at these things with an instrument that can sense the ionosphere, like, for example, in this case, the Arecibo Incoherent Scatter Radar? You see very large fluctuations, for example, sometimes that occur on the bottom side of the ionosphere. This is altitude versus time here, and if you look at the middle plot, the dashed line is the electron density variation at the F2 peak. So that F2 region that Carl was talking about, there's 50% of fluctuations from the background during especially intense large-scale TID. Why large scale? Because it's got a wavelength of over 1,000 kilometers. But we're going to concentrate on the amplitude. And well, I'm not showing you, but you can look at gravity waves have a downward phase progression, and that actually conclusively identified this source as acoustic gravity waves coming from the lower atmosphere, stuff from below. So 50% of background for this particular example. Whoops. This is an example at mid-latitudes, the subject of this conference. Right hand is the Millstone Hill Incoherent Scatter Radar, which we operate at Haystack. The one on the left is the Kharkov Incoherent Scatter Radar over in Ukraine. And these are the electron densities at the top. If you detrend them and you subtract off the background, you get, and this is delta NE in fractions. So if you translate that, that's up to 20% of the background density fluctuating. Nothing was happening geomagnetically here. This was quiet. There was no high latitude forcing. This is basically lower atmosphere forced. It occurs almost every day at some level. And this is time periods of 40 to 80 minutes. But the important thing is amplitudes up to 20% of the background density. So why am I saying all this? Well, let's do the thought experiment. Let's work the most extreme natural forcing event we can think about, which is the Tohoku earthquake. This was a terrible event. This was an M9.1. You may have read about it at the time, caused untold amount of death and property destruction. Question is, how big is the ionospheric perturbation and what effects may this have on HF propagation? Not higher frequency stuff, the really heavily refracted stuff that HamSci often concentrates on. And the little quote there is an encouragement for you to read John Allen Paulos's book about innumeracy. We're trying to be numerate here. We are trying to see what this factor is compared to other things. So this is a paper by Attila Kumjati at Jet Propulsion Laboratory that talked about the Tohoku about a year after it happened. This is a detrended receiver. We've subtracted the background. This is total electron content, integrated amount of electrons above the receiver in Usuda, which is about 400 kilometers from the epicenter, which was off there's the southeast in the ocean to the southeast of Japan. There's the tsunami signature that Carl talked about, and then there's the traveling ionospheric disturbance. Look at the scale. We're talking about plus or minus 1 to 1.5 TeQ. By the way, the relative uncertainty of this instrument is very precise. It's about 0.01 TeQ, so this is not noise. This is very significant. These are detected plenty well by sensitive TEC receivers, not at HF, up at 23 centimeter wavelengths, or 1296 megahertz and above, where the atmosphere is transparent. The radiation pretty much goes right through and you can sense minute fluctuations. So very well detected by these professional instruments. There's another model of it. This is a model that is driven by the actual data taken near Usuda. This is another first principles physics model, but if you look at the wiggles and if you have really good eyes and you look at your scale, once again, we're talking about 1 to 2 TEC unit perturbations. So let's continue to be numerate. What's the background? This is a map from our data source at Haystack showing worldwide total electron content. This is in a log scale, so it's a little bit hard to interpret at first blush. This is the Japanese area. Just as a reminder, 1 TEC unit is about 10 to the 16th electrons per meter squared in a column above the spot. So I'll make it a little easier for you. Let's change that to linear and zoom in. So this is Japan. I'm pointing to the Usuda station right there. If I look at the numbers and I average them, it's about 29 TeQ, 29 TEC units. Remember, the perturbations were 1.5 TECU worst case. I divide that out and the relative perturbation is about 5.2% for a 9.1 magnitude earthquake. Very detectable in TEC. There are other examples of this. This is a paper from the Irkutsk group in Siberia. This is Ed Efremovich and colleagues showing an earthquake in Turkey. Again, the sensor is a few hundred kilometers away. This is the Hickey paper from 2006 and a volcano eruption in 2004. And if you look at those wiggles, we translate them to relative, we're talking about 1 to 3% perturbation amplitudes. So again, the Tohoku was about 5%. These are in the couple percent. So let's continue our thought experiment then. So there's an example. Notice that storm time TIDs are 50% amplitude. Quiet time can be up to 15% amplitude. And one of the largest things we found was 5%. So it turns out that I can't disambiguate the earthquake signatures from the normal day-to-day variability that happens. I can do it with calibrated instruments. So the question is, what if I look at HF signal propagation? I'm going to conclude with that. Can I see this kind of effect? It turns out that there are localized effects on these large traveling ionospheric disturbances, and this paper, which includes, by the way, as a co-author, Mike Rahanami, who's going to be giving our tutorial tomorrow on mid-latitude physics. It turns out that if you have a modulation of electron density similar to this in the upper atmosphere, you get focusing and defocusing of the rays on the ground as they bounce off that structure. So where I've circled, you might have a local hot spot where the amplitude would go up, and then as that wave would move by, maybe the amplitude would go down. Carl referred to hearing fading. Anybody who's listening to a shortwave broadcast signal from overseas will hear sometimes fading. A lot of that can be driven by TIDs, but it's localized, okay? It's not necessarily a wide-scale event. These kind of TIDs are the subject of upcoming investigations in our community, as other people have talked about, and that, as we'll be doing, I leave the reference to Nathaniel Frizzell's 2014 paper as an example. So let's just, again, conclude this with a thought experiment. I'm going to assume there's someone in Seoul, South Korea, who is transmitting pretty much due east, and I'm going to put the midpoint of that contact point over Usuda, somewhere within the largest perturbation zone of the Tohoku event, as I showed you from the paper that Attila published earlier. What happens to HF propagation? I'm going to use the FarLap ray tracing engine here. The top is the pre-earthquake propagation. I've launched a number of rays, and you can look at where they come down. Some of the high-angle ones transit the ionosphere and leave. Some of them, of course, bounce down to the ground and may hop again. This is just one hop. The bottom is if I increase the electron density by 5.2% everywhere. It's pretty hard to find the difference. So in that case, there really is and I don't know of any wide-scale propagation event. If I'm looking at an individual station, sure, I might be able to get a little bit of focusing or defocusing, but I don't think there's a wide-scale event, and certainly not anything I can determine from other natural variability that's happening any day of the year. Finally, I'm going to show you 21 megahertz, where, in fact, if you look at the ray trace down at the bottom, again, exactly the same thing. You will notice that there's a little bit of focusing beginning to occur there. So some of that effects that Samson talks about would in fact occur, and I'm not putting in a wave in here. I'm just literally lifting. I'm increasing the electron density everywhere. So just to summarize and to kind of wrap this up from what Carl was saying a little earlier is that we know for sure that the ionospheric electron density is variable in any day of the year, and even more prominently at storm times. Gravity wave forcing from below, and then, for example, energy input from above through things like coronal mass ejections or CIRs. And there are natural transients, which I've shown can be easily measured by professional equipment. HF propagation variability includes contributions from all of those sources, but just an amplitude alone, I can't disambiguate the earthquake signatures or volcanoes or what have you from natural day-to-day variability. And so the question of what and how much is in fact a frontier topic. Things, including in HamSci, will help us quantify the forcing from below versus forcing from above, and we're right in lockstep with all the frontier talks that I always hear at places like AGU. So K9LA and W1PJE, both thank you for listening, and I'll put this up as an acknowledgement since we used FarLap and also the International Reference Ionosphere, and then the ITU recommendations for radio noise for those particular propagations. So I'm going to stop there, Christina, and let's see if there's any questions, I guess.
All right. Thank you, Carl and Phil. That was excellent. Let's see. We are a few minutes ahead of schedule. We've got Claire up next. Any questions, please put them in the chat.
Yeah,
Great.
can I ask a verbal question?
Go ahead, Dev.
Hi, Deb. Sure, go ahead.
Yes. So perhaps I missed it. So how did we determine that the earthquake would lead to increase in the TEC values?
Okay. So there's essentially there's a wave structure that gets launched. The research is that there is a wave structure that gets launched because of the fact that you're basically almost forcing the lower atmosphere like a piston. Okay, so whether it's a fertilizer explosion or whether it's a volcano or whether it's a earthquake, you are sort of forcing that column of air, which is an enhanced generator of gravity waves. And
Mhm.
then the primary and secondary and tertiary braking process that I talked about
Mhm.
um, is the thing that will then trigger a large scale ionospheric disturbance. So that's where the TID source comes from. And you saw that in the GPS data. Um, the message we were trying to get across, I think, is that you got to use the right technique to look at it. Using a highly refracted HF technique is not necessarily always, it'll show you the fluctuations, but in a different manner that, for example, a higher frequency GPS measurement would.
No, that's what my question was. Okay, so there is a primary, secondary, tertiary uh, gravity wave disturbance process. My question is, why should that necessarily lead to an increase in TEC values? TEC is necessarily
Uh,
integral between 2 points, and why
okay.
why why should it increase, not decrease, for example?
All right. So
Let me
what's
let me
happened here is
let me
my
complete.
thought experiment has led you to another conclusion. I did not mean to indicate with my thought experiment that every piece of TEC went up. I'll be very direct. This was me having very little time to run the simulation. And what I should have done, of course, Deb, is put in an oscillation in TEC above the background that was, for example, the 5.2%. Not having time for that, I just wanted to make sure that I wanted to see if I lifted all of the TEC, again, not realistically, by 5.2%, could I tell in terms of general HF refraction over a wide area whether that had occurred? And then the answer was not really. But if I had put a real TID and simulated that, sure, I would have seen bunching and defocusing and focusing similar to what Samson did. So sorry, I may have confused you a little bit there in my little thought experiment.
Okay, that's fine. Finally, again, uh, so for example, if there are irregularities, depletions in the ionosphere, why should I be expecting an increase in TC value whenever there I know for sure that there are depletions, or should I be expecting increase or decrease in TC values whenever there are depletions in the ionosphere?
I I don't know there's a general answer to that question because it really depends on the physical processes involved. Yeah, I kind of have to know more about the situation. I don't really have one size fits all sort of answer to that, at least from me.
Thank you.
Sure.
Thank you so much.
Is there any other question in there, Christina, that you or the moderators, whoever the moderators are, and maybe one for Carl? You know, he's on the line too.
Oh, that's okay.
Liz,
I'm
Liz McDonald, I have read your comment. Yeah, I'll try to use
I
the
have a
1,000
question, Phil.
most common words.
Yeah.
Yes, go ahead.
You know, people when they are listening to the radio or operating, and you see all this variability, and someone might wonder, where does it come from? What are some logical steps for properly diagnosing or where these disturbances are coming from?
Right.
What is a good method for going about making a logical conclusion, or
And
or saying even I don't have enough information?
right. Um, all right. One thing comes to mind here, and which is that in space physics, when we laid out professional instruments, we long ago learned that the space-time ambiguity is a problem. Because if you measure at one location and a wave goes by you, it is very difficult to determine whether that is a wave propagating by you causing something to fluctuate, or whether that is a production loss that is actually causing the place that you're looking at to go up and down. When you add more views, okay, to the picture, you look in many more directions, you end up resolving that. And that is, in fact, the very basis behind why those total electron content maps were so revolutionary when they showed up, is because you were looking in many directions at once, and you were able to look at two-dimensional snapshots as a function of time. So the response I would have to you, Nathaniel, is that if you deploy a widely distributed HF network where you are getting these different ray paths, you start to disambiguate that. So it's the collective effort of many people observing at once on coherent timescales, so you know when you measured, right? And then backed by a good model, as for example, we heard from Steve Kepler, of what's happening refractively here. It's not only a challenge, but that's the opportunity to disambiguate these things.
And then also using other instrumentation as well, right? Not
Absolutely.
just HF.
That's
but
right.
Know what the geomagnetic field is doing, know what the TEC is doing,
Correct.
know what the solar wind and the IMF are doing. All of these things together help to form a more complete picture.
Correct. And also, going back to my numeracy point, understanding the magnitude, the 1, 3, or 10, as we like to say in physics, right, of the various effects, and understanding that, for example, on a background of field of 30,000 nanotesla, a 100 nanotesla perturbation, which may be very significant in some contexts, may not be that significant in the context of the relative perturbation in terms of the background field. So it really depends. It's like where you always have to start being numerate, like, does this effect matter? Where am I in the order of magnitude scale? So I encourage anybody to even step back if you've been doing this for a while like I am, and that's honestly why Carl and I did that, to just ask the basic question, wait a minute, let's just do a sanity check here. And that's where that other data that you talked about, having a fusion kind of large scale approach, is the way that you can get that clue.
Yeah. Now, another question following on to, I think, what Dev was trying to ask, with the total electron content, let's say the waves are just moving the ionosphere up and down.
Right.
That's not necessarily changing the total number of electrons in the column. It's just moving them vertically up or down.
Sure.
Why would that affect the TEC?
Well, okay. TEC is an integrated quantity, right? So it is sort of a sum all the way up. So in some sense, if the TEC is changing locally, right? Well, yeah, that's probably, if a wave is going by, I'm thinking, and if the TEC has gone up, that could mean, for example, that the profile has not stayed the same shape as it's gone up, but that something has removed either some of the top or some of the bottom or sent it somewhere, which would indicate transport, right? That would indicate that now I'm moving it from where I am to where I'm not, but I would lead then back to the idea that says, now I got to be looking everywhere or as many places as I can so I can see that particular thing happen.
Yeah, right. And how about vertical transport? Can, when you move the neutral atmosphere, even the ionosphere vertically up or down, that can change the chemistry at that particular height.
Yes.
So it might change the recombination rates or the production rates. Are those rates on a fast enough time scale that just that vertical motion could change the TEC?
Yeah, if we want to be numerate about it, then that's where you get out things like the various collision frequency rates between the different species. So we should say one thing very quickly for those people who haven't thought about this, is that in the neutral atmosphere, we're living in a place where the air is well mixed. There's a standard atmosphere if you go out and grab a box of air, right? At the altitudes we're talking about, we are no longer, we're above the turbopause, so everything is sorted by mass. So as you go up, the atmosphere is changing, the different species are changing, the heavier stuff is falling off faster. So the chemical recombination is changing. So yes, if you lift the profile up, then if you keep it there long enough, then sure, you're preserving density. But that is not necessarily going to happen on minute time scales. That might take, half an hour, 45 minutes, something like that.
Right. There's a question in the chat. Thanks, Bill, for pointing this one out to me. This is from, let's see, Jim Bacon. He asks, how much of the TEC difference is in the F region, and is some of it a contribution from the E region?
Thank you, Jim. Once again, we're talking about an integrated quantity, right? We're integrating all the way up. My very, very simplified, and Svera seems to have his hand up as well. Hang on one sec. The
No,
conventional wisdom.
I have a separate question, so it comes.
Okay, great. The conventional wisdom is that, you know, a good portion of the TEC, maybe half of it, maybe more, is coming from the F region if you just do the integral. Okay. If the E region gets big enough, sure, that could start contributing to the integral. At the levels we're talking about, a few percent, Jim, I could not say one way or the other whether, in fact, maybe that is some of the E region becoming more prominent. That's getting back to the change in the profile. So, you know, like my friend Joe, who you will hear about tomorrow, says this is a big DOF experiment, one thing with many variables, and our challenge is to get the relative amounts right. Sphere, I don't know, Christina, do we have time for one?
I'd like to hand it over to Claire soon. So if it's a quick one, go for it. If
Yeah.
not, then maybe best handle in the chat.
Okay.
It's a quick one, probably
for
to Carl. But there was mention here that this traveling ionospheric disturbance results in fading. Now, fading can be slow and fading can be rapid. Is there any correlation between these? I mean, fading can also be something with the ordinary and the extraordinary wave interfering with each other. So is there any way we can sort of separate one from the other of these mechanisms and, in how we hear the fading?
Okay, so I'm going to give you a very quick answer to a very complicated question. First of all, I think Professor Rahanomi tomorrow will be talking about mid-latitude physics. And one of the things he'll be talking about is mid-latitude irregularities, which we honestly didn't know very much about at all until that recently. Fast fading could be due to little bits of changes in reflections from embedded irregularities the signal is coming through. If you're talking about fading on a 10-minute case, 15-minute case, you know, longer than that, that is a little bit better argued as a traveling ionospheric disturbance going through, because we happen to know from things like TEC maps that the typical periods of those waves are 20, 30 minutes with wavelengths of a few hundred kilometers. So there may be an opportunity to disambiguate in that sense. But again, you got to throw as much observational information at it as you can.